look at section 6.1, 6.2, and then I have some sample problems from the homework and quiz, actually homework and applications assignments that we have this week. So just like I've done in previous weeks, we'll take a look at problems that students struggled with last semester. And as we're going through 6.1 and 6.2, we'll also do some examples. So the first thing that we're going to start with is some definitions. And the first definition that we're going to talk about is an algebraic expression. So really pay attention to expression here, okay? And an expression is just a combination of letters which represent variables or unknown values in algebra, and then numbers, which we're used to, of course. And then we can combine these using addition, subtraction, multiplication, division, powers, roots, all of those things. So below here, you see some examples. X plus 6, so we've got a variable and then a number, and we're combining them with an addition sign. Here we have x squared minus 6, so we're combining a variable and a number, and we're using both a power and a subtraction, and so forth. So these are all expressions. And notice that while they have add, subtract, multiply, divide, powers, roots, or some combination of those, there's no equal sign. An algebraic expression does not have an equal sign. So we can't solve it. We'll come to that in a little bit, but there's no solving an algebraic expression. What we can do is we can evaluate it. So if you think about the word evaluate, what evaluate means is I'm going to pick a value for x, and then find the value of the expression. So for example, if I want to evaluate 6x, I'm going to say, let's evaluate 6x when x equals 3. And what I'm going to do is I'm going to replace this x with this value. So that's going to be 6 times 3, which is equal to 18. So when I evaluate 6x, the expression, for the value of x equals 3, I get a value for the expression of 18. But we didn't solve anything yet. That will come later. We'll get there. So when you are evaluating, we're going to just use that order of operations. So we always start with parentheses. We work from the innermost parentheses or any grouping symbols that we have. So it could also be brackets or braces or absolute value signs. And then we work from the inside to the outside. Also remember a fraction bar, the numerator and the denominator, we just pretend in our head that they're enclosed in parentheses, and we do those first before we take care of the fraction bar. So parentheses or any grouping symbols, 2 is exponents, 3 is multiplication and division. Remember, we're working from left to right. So if there's a division to the left, it's going to happen before the multiplication. Same thing with addition and subtraction. They come after multiplication and division, and we work them from the left to the right. So here's another example of evaluating. Remember, we're not solving, we're evaluating. We're finding the value of this expression when x is equal to 6. So all we're going to do is replace this with a 6. So first I'm going to rewrite this entire expression, replacing x with the value I was given here, 6. And then I'm going to use that order of operations. So the first thing that I see here is some parentheses. So I'm going to work inside those parentheses. I'm going to leave everything else alone. 6 minus 4 is 2. So I'm just going to replace that. The next thing that I'm going to do, my order of operations says next is exponent. And I have an exponent right here. So I'm going to evaluate this expression. And 2 cubed is 2 times 2 times 2. which is 4 times 2, which is 8. So I'm going to replace this 2 cubed with 8. And now the next thing I'm going to do is any multiplication and division. And remember the parentheses here are an implied multiplication sign. So that's the next thing I'm going to do. I'm going to copy everything else, and then I'm going to do 5 times 8. And now I'm down to just one operation left, so I'll go ahead and do that addition, and I get 47. When I evaluate this expression for a value of x equals 6, that expression is equal to 47. And it would have a different value if I chose a different value for x. Now, an equation has an equal sign. An equation is formed when we take two algebraic expressions. So maybe 3x plus 2, that's one expression. And then here's another expression, 5x minus 17. And I put an equal sign between them. That is an equation. So an equation has to have an equal sign. A formula is a special type of an equation. It has two or more variables. So let's see, volume we know is length times width times height. So we actually have 1, 2, 3, 4 variables. This is a formula. With a formula, as long as I know all but one of the variables, I can plug in all the other variables and I can solve for the missing variable. Remember I said we were going to come to solving. When we have an equal sign, if we have only one variable missing and the rest are all numbers, then we are able to solve an equation. And then we have mathematical modeling, which is when we try to find a formula that describes something in the real world and then use that formula to solve a real world problem. And here we have an example for a variety of age ranges, so 4 to 8, 9 to 13, and so forth, up to 51 and above. And notice that they are given group numbers. So this is group 1, 4 to 8-year-olds, group 2, 9 to 13-year-olds, and so forth. And then in the pink bar, we see the calorie needs to maintain energy balance for a moderately active lifestyle, which they're defining as walking between 1.5 and 3 miles per day at a rate of 3 to 4 miles per hour, and then doing some light physical activity. So a moderate lifestyle. So you can see that for 4 to 8-year-olds, both males and females require about 1,500 calories. And then as the groups get older, the males require even more. And then, no, the males are always requiring, doesn't really drop off that much in older ages either. So this is a model of the caloric needs for humans, male and female, from 4 years old and up. And then we have this equation models that. And the way that this equation works, so whenever you see an equation, you have to look for the variables and you have to see what is each variable representing. So in this equation, we have an f. So I want to know what the f represents. And then we have an x. And the x is used both here and here. So to understand this equation, we need to know what is x and what is f. Well, f is the number of calories needed per day. Okay. And x is, for females, and x is the age group that they're in from, I think we had 5 of them, from 1 to 5. Were they in age group 1, 2, 3, 4, or 5? Let's look back here so we can remember. Okay, yes. Oh, 6 age groups. So group 1, 2, 3, 4, 5, or 6 is what we're. So X is going to be 1 through 6. So you give me a number, the age group that you're interested in, 1, 2, 3, 4, 5, or 6. I plug in that value here and here, do all of these calculations, and then F will come out, and that will represent the number of calories needed by a female in that age group. So we can take a look at a value for the 19 to 30-year-old group. And the way that we would do that is we would go back here and say, which group was that? 19 to 30 is group 4. So I'm going to take that equation here, and everywhere I see an X, I'm going to replace the X with a 4. So negative 66 times 4 squared plus 526 times 4 plus 1030. That's step 1. Step 2, I'm going to go ahead and do this exponent. So 4 squared is 16. In my next step, I'm going to go ahead and multiply all of these. So I have negative 66 times 16, which gives me negative 1056. Here I have 526 times 4, which is 2104. And then I'm just going to copy down the 1030. And then finally, I'm going to add these all up. So remember, this one is negative. So when I add a negative and a positive, I really take the difference of these two. And then since this is bigger, I'm going to keep the sign on this one. And when I add all of these up, I get 2078. So that indicates that for a female in the 19 to 30 age group, that person in that age group would require 2078 calories. How does that compare with our picture? Oops, I'm going the wrong direction. Let's go back. Here we go. So we came up with 2078, pretty close to that 2100, which was listed here. Okay, so remember, all we're doing here is just plugging in a value and then seeing what comes out. A little bit more vocabulary that we're going to look at. When we have an expression, we break an expression into individual parts, and we call each of those parts terms. And the terms are separated by addition. Remember, when we talked about positive and negative numbers, we said that we can think of this as 7x plus negative 9y plus negative 3. So subtraction is the same as adding the opposite. So if I'm subtracting 9y, it's the same as adding the opposite, negative 9y. If I'm subtracting 3, it's the same as adding the opposite, which is negative 3. So these are the individual terms. 7x, let's underline those with a different color here. So 7x is a term, negative 9y is a term, and negative 3 is a term. Those are the terms. Okay. The coefficient is the numerical part of the term. So in this term, the numerical part is 7. In this term, the numerical part is negative 9. And in this term, the numerical part is negative 3. So we can also say negative 3 is a coefficient. A term that only has a number, it doesn't have a variable part, is called a constant term. So that negative 3 is also a constant term. And we say it's constant because it will never change. Doesn't matter what x and y are, this is always going to be negative 3 because we're not multiplying it. This value will change depending on y, and this value will change depending on x. But this one, the negative 3, is always constant. And then we have terms that have the same exact variable factors, and we call those like terms. So 7x and 3x are like terms because their variables are the same. But here we have 7x and negative 9y. Those are not like terms because their variables are different. Another one to kind of think about is, what if I had something like x, let's call it 3x squared, and 4x cubed. Well, these aren't like terms either because this one is squared and this one is cubed. So both the variable and the power have to match. And then the factors are just the part of each term that are multiplied. So for example, in this term 7x, the factors are 7 and x. In this term negative 9y, the factors are negative 9 and y. So make sure that you understand all of those terms, all of those vocabulary words. I don't want to call them terms because that gets confusing with what a term is in algebra. Another thing to pay attention to when you are simplifying expressions or solving equations is some properties of real numbers. And you maybe remember these from another math class that you've had. This first one tells us that we can both add and multiply in whatever order that I like. We call it the commutative property, and it works for both addition and multiplication. So for example, a plus b is the same as b plus a, or 3 plus 2 is the same as 2 plus 3. So if I am adding two numbers and I don't like the order that they're written in, I can rewrite them in the other order, and I know that I'm going to have an equivalent expression. So I haven't changed the value, I've just changed the form of this. It also works with multiplication. A times b is the same as b times a. And then we can extend this idea, and that's called the associative property, and it also works for both addition and multiplication. And that tells me if I'm adding up three numbers, it doesn't matter which two I add first. So 1 plus 2 plus 3, I can first add 1 and 2 together, and then I have 3 plus 3, which is 6. Or I can first add 2 and 3 together, and I have 5. Then I add the 1 and I get 6. So when we combine this commutative property and the associative property, that tells me that I can add numbers in any order that I like. And this can be really useful if I'm adding up a string of numbers like maybe 1 plus 7 plus 9 plus 3. I might in my head say, oh, well, I've got 1 and 9, that's 10. And then I've got 7 and 3, that's 10. So 10 and 10 is 20. And it just makes it a little bit simpler than adding up. So this is good. These are useful for mental math, and they're also useful when we're evaluating expressions and solving equations, because we often want to change the order. And these properties tell us that when we change the order, we haven't changed the value. And that's important because we don't want to take an expression and rewrite it in a way that changes its value. And then if we're going to stick this equal sign in there, we want to make sure that indeed they're equal. And then we have one more property that combines addition and multiplication, and we call this the distributive property. So if I have to add up two numbers and then multiply them by a third number, I can do it in that order, but I can also multiply each of these numbers in here by this outer numbers. And we sometimes draw a picture like this to show what we're doing. And here's another example of drawing that little picture. And we use this a lot when we are simplifying expressions. It also works here with subtraction, because when we think of this subtraction, remember, we can think of this as just b plus negative c. So that also works. And we'll be using these properties when we start simplifying. And so remember, this is an expression because there's no equal sign. And the instructions say to simplify. So that means, can we write it in a simpler form? And the first thing that we can do is we can distribute this. So we're going to take 5 times 3x, which is 15x. And then I'm going to take 5 times, remember this sign has to go with it. So 5 times negative 7, which gives me negative 35. And then I'm going to copy down that minus 6x. And then remember, we said that we can think of this as 15x plus negative 35 plus negative 6x. And so the next thing that we want to do is we want to look for like terms, terms that have the same variable and the same power. So here's one, and here's one. And we can combine these. And we know the commutative and associative properties tell us we can add in whatever order we like. So we're going to add these two together. So 15x plus negative 6x, which gives me positive 9x. And then I still need that plus negative 35. And so I probably would just leave this as 9x minus 35. We don't usually, it's simpler, isn't it, to write minus than to write plus negative. That's what we had for this one. That's the end of 9.1. So we'll go ahead and start up with, sorry, that was 6.1. Confusing myself which class I'm in here. 6.1. Now we're going to look at 6.2. So we're going to look at solving linear equations that have one variable. So what do we mean by a linear equation? A linear equation has an x, but it doesn't have any powers. Okay, so it has x and it can have multiple terms on on both sides or either side that have x's in them, but it just can't have x's that are raised to the power. And then the a and the b there are just representing real numbers. And of course, a can't be 0 because then we wouldn't have an x. So when we solve an equation, what we want to do is we want to start with our more complex equation and continue to write equivalent equations that are in a simpler form until we get to the very simplest form of all, like this. This is still a linear equation. It has an x and it has a value. So this is the very simplest form. And this is what we're trying to get to. This is our end goal. And as long as we continue to use operations on both sides that give us an equivalent equation, then we know that we'll have the same solution. What do we mean by a solution? We mean values that when we replace the x, give us a true statement. And we call them either a solution or a root. So in this example, you can see that -3 is a solution to both of these equations, because in this one, if I replace x with -3, I get a true statement. 4 times -3, which is -12, plus 12 is 0. So this is true. And then if I replace this one with -3, I get -3 equals -3, also true. So these are equivalent equations because they have the same solution set. The same x values make them true equations. And we're going to use a couple properties of equality to help us solve these. So when we're solving an equation, we start with that more complex equation. We continue to write equivalent equations using these properties until we get to that very simplest form that looks like x equals whatever the value of x happens to be for that equation. The addition property tells me that if I have two numbers that are equal, and it might be a little bit easier to think about, 3 is equal to itself, right? So if I start with something like this, I can add anything that I want to both sides. Let's add 5 to both sides. Still true, right? So we had 3 equals 3, and we made it more complex by adding 5 to both sides. And now we have 8 equals 8, or 5 plus 3 equals 3 plus 5. But I can go in whichever direction I like, as long as I do the same thing to both sides. And the way that we apply this to solving is that we're going to use this property to give us a simpler equation. And we'll see how we do that in the next slide. We can also do this with multiplication. And again, think about starting with, do 2 equals 2 this time. I can multiply both sides by 5, and now I have 5 times 2 equals 5 times 2. Still true. 10 equals 10. Okay. So true, and as long as c is not equal to 0. If c is 0, we set ourselves up for some problems. So we want to make sure that we're multiplying by a non-zero number. And remember that subtraction is just adding the opposite. So I can also subtract the same number from both sides. Also multiplication, or sorry, division is multiplying by the reciprocal. So dividing by 2 is the same as multiplying by 1/2. So that means that I can also divide both sides of my equation. So as long as I am doing either this adding the same amount, subtracting the same amount, multiplying or dividing by the same amount, I'm not changing the solution of my equation. I'm only changing the form of the equation. So how do I know what I want to do to both sides? And we're going to start with something simple. So I think a lot of students look at this first one and they're like, well, I know that X has to be 11. So slow your brain down for a minute and let's figure out, how we know that. So if we apply that property of equality, what would I want to add? Well, if I add 3 to both sides, what happens here? I have -3, +3. Those cancel each other out. So on the left side, only the X remains. And then on the right side, I have 8 + 3, which is 11. Okay. For this one, the side that has the X has a +7. So I'm going to subtract 7 from both sides. When I both add and subtract 7, I'm left with just an X over here. And over here, I have -22. I can also do the same thing here. So here I have 6 times X. So what do I want to do to get rid of 6 times X? I want to divide by 6. If I divide this side, I also have to divide the right side in order to have an equivalent equation. And then these cancel to give me X. 30 divided by 6 gives me 5. When I'm dividing X by a number, what do I want to do? The opposite of division, which is multiplication. So I'm going to multiply both sides by 5. Here, remember, if it helps, you can think of this as 5 over 1. So this would give me 5 times X over 5 times 1. And then the 5s would cancel, and I'm left with X. On the right side, I have 5 times 9, which is 45. And if you do everything right, when you take that solution, so in this case, this solution was 11, and you replace the X with that solution, it should give you a true equation. 11 minus 3 equals 8. That means I solved it correctly. For this one, I should be able to take -22, add 7, and I get -15. So I did that one right as well. That's the way that you can check your work on these. So to solve a linear equation, we have a little procedure here. The first thing that you want to do is you want to simplify the expressions on both sides of the equal sign. And we're going to do that like we did in the previous section. We're going to remove the grouping symbols, parentheses or anything like that, and then combine like terms. Once we've simplified both sides and made those expressions as simple as we can, we're going to collect all of the variable terms on one side and then all of the constant terms on the other side. And we do that by using that addition property. Let's go back a page. We're going to use that addition property. So if I have an X, or sorry, if I have numbers here and here and I only want X's over here, then I'm going to add 3 so that this moves. And we can do the same thing with X's. So if I had X's on both sides, I could subtract X from one or from both sides and get the X's to go to the other side. And then once I've done that, I isolate the variable, and that's where my addition and subtract, or my division or multiplication comes into play. And then finally, I do what we were doing on that last step where we take the value, the solution, plug it into the original equation, and make sure that we have an equation that is true. So let's see what that looks like. We have 2 times x minus 4 minus 5x equals -5. So the expression on the right is as simple as it gets, but this expression we can simplify. And the first thing that we want to do is to distribute this. So we have 2 times x, which gives us 2x. and then 2 times -4, which gives us -8. And then we're just going to copy everything else down, the -5x and the -5. The next thing that we're going to do is we're going to combine the like terms. And you can see that we have an x here. Whoops, sorry. Let me undo that. We have an x here and an x here. And when we combine these two, we get 2x minus 5x, which gives us -3x. Everything else gets copied down. We keep the -8, we keep the -5. Now we have this expression on the left is as simple as it gets, and this expression on the right. So we've simplified both sides. The next thing that we're going to do is we're going to say, how do I get rid of this? I have x's here, so I want to get rid of the part without x that doesn't have x's here. So the opposite of the opposite of subtract 8 is add 8. So I'm going to add 8 to both sides. And remember that we had this equation, we added 8 to both sides, so we haven't changed the value of this. We've only changed the form. Now we add these together, they cancel, and we're left with -3x on that side, and then on the other side we have 3. Our last step then is to get rid of that -3 that's in front of the x. And let's pull up the next page. So we had -3x equals 3. And what we're going to do is we're just going to divide, and this is actually a little typo here. We have to divide by -3. So when we divide by -3, this side we're left with x, and on the right side we have 3 divided by -3, which is -1. So we've written now an equivalent equation. It's equivalent to the first one, and it's the simplest type of equation of all because it tells us the value of x that we can plug in here and here into the regular or the original equation in order for this equation to be true. And this is how we check our work. So we take that -1, and I'm going to rewrite this where the x is. I'm going to put a -1. So I've rewritten everything else. 2 times -1 minus 4 minus 5 times -1 equals -5. When I simplify, this is going to give me -5. -5 times 2 gives me -10. And then I have minus -5 here. And -10 minus -5 is the same as -10 plus +5, which is -5. So this checks out. This equation that we started with has a solution of -1, and this equation that we ended with has a solution of -1. So that means they are equivalent, and the solution to our original equation is the same as our simple one, -1. We're going to look at an application now. So we have these graphs that are showing, based on the intensity of a negative life event, so a low intensity event with an intensity of 1 all the way up to a high intensity event with an intensity of 10. This shows the average level of depression on a scale from 2 to 18. And for groups that have a low sense of humor versus a high sense of humor. And then we have equations that model these. So in the low humor group, if you tell me how high the intensity of the life event was, I can plug in that value here for x, and then out will come the value of the level of depression. And then we have a similar equation for the high humor group. So if we have for the low or for the high humor group, we have a negative life event with oh no, we want to know what would be, we're going the opposite direction. So D tells us the depression level. We're given a depression level of 7/2, which means we're going to replace this with 7/2. And we want to know what's the intensity level, which is represented by x. So that means I have to solve this equation. 7 over 2 is 1/9 x plus 26/9. And to solve that, I'm going to first get rid of these fractions. And I do that by looking at all of my denominators. I've got a 2 and a 9. And then I'm going to find the least common denominator. They don't have anything in common, so the least common denominator is going to be 2 times 9, which is 18. And then I'm going to multiply both sides by 18. And the reason I do this is to get rid of those fractions. What happens when I multiply 18 times 7 over 2? Well, we can think of this as 18 over 1 times 7 over 2. And then, of course, you can use your calculator. We can also do a little mental math and divide both 18 by 2 and 2 by 2. So we're left with 9 times 7 over 1, which gives us this 63 over here. When we multiply this by 18, we're going to have to distribute. So we've got 18 times 1/9 x, that's here, and then 18 times 26/9. We can do that same thing again. Think of this as over 1. Now I can divide both the numerator and the denominator by 9. So this becomes 2, and this becomes 1. So I have 2 times 1 over 1, which is 2x. That's this term. And then lastly here, I can divide 18 by 9. That gives me 2. 9 by 9, that gives me 1. So I have 2 times 26, or 52 over 1, which is just 52. And now I can solve this by using that addition property of equality. And what do I want to do? I want to add negative 52 to both sides. So if I think of adding negative 52 or just subtracting 52, same thing. Over here, I have 63 minus 52, which is 11. Over here, I have 2x plus 52 minus 52, which leaves me with 2x. And now once I have that equation to this point, remember to get rid of this 2 times x, I'm going to divide both sides by 2. So that means the intensity that yields a depression level of 7/2 for the high humor group would be 11 over 2, which is 5.5. All right, so let's look at a little bit more complex equation here. So on the left side, I'm as simple as I can be for that expression. But on the right side, I can distribute. So I'm going to go ahead and do that distributing 2 times x for 2x and 2 times 4 for 8. Once I get to here, remember, I only want x's on one side of the equation. So to get the x's, what I'm going to do is subtract 2x. Well, what happens when I do that? I get these 2 x's to cancel, and I'm left with 6 on the right side, and the 2 x's over here on the left side, and the 2 x's here cancel, and I'm left with 8. That gives me this equation, 6 equals 8. And then I think to myself, when is 6 equal to 8? Well, if the answer is never. 6 is never equal to 8. And what that tells me is that since this equation and this equation, these are equivalent equations. And they're equivalent because all of these operations that I did, I proved that I can do these. Those are those properties that we have. As long as we add or subtract the same thing from both sides, we have an equivalent expression or an equivalent equation. So if these equations are equivalent and this one is never true, that must mean that this one is also never true. And what that means is it doesn't matter what x is. There's no value of x that will make this true. It will never be true. And so we sometimes say no solution, or we might write the solution set like this, an empty set of braces, or we have a special symbol for that, which is the 0 with a line through it. We call it the empty set. So these are 3 ways of saying that there's no solution to this equation. Let's take a look at this equation. The left side is as simple as it can get, but the right side I can simplify again by distributing. So we'll come down here. So 6 times x gives me 6x, and 6 times 1 gives me 6. So I have 4x plus 6 still on the left. On the right, I have 6x plus 6 minus 2x. And I can combine these two terms to give me a 4x. And notice what we have here. We have 4x plus 6 equals 4x plus 6. Well, that's always true. It doesn't matter what value you pick for x. You can plug in any value of x that you like. 3,152,813. Doesn't matter, any value. This is always true. And because we use those properties, we know that these two equations are equivalent. So whatever makes this equation true makes this equation true. So that means this is also always true. And so we write that. We sometimes just say all real numbers because we can plug in any real number that we like and it will work. And then if we want to be really formal, we write it like this, which is read the set of all x. That's what the little x with the bar and the x means. The set of all x. This means such that x is a real number. That's another way of writing that in set notation. The last thing that we're going to look at are ratios and proportions. So a ratio is just a comparison of two quantities by division. And we sometimes will write a ratio like this, 1 to 3. We might use words, 1, 2, 3, or we might use a fraction bar. These are all equivalent ratios. And to make it a proportion, so this is a ratio, to make it a proportion, I need an equal sign. So 1/3 is the same as 2/6. That is a proportion. When we have variables in our proportion, we can solve them. So if I have a proportion like this one, 63 over x equals 7 over 5, then we can use what we call the cross product principle. This only works when we have an equal sign, okay? So we only use this cross products principle when we have an equal sign. And what it tells us, let's go back to the one we know that 1/3 is equal to 2/6, right? Because we can multiply the numerator by 2 and the denominator by 2. So they're equal. So look what happens when I multiply, I get 1 times 6 is equal to 2 times 3. Sure enough, 6 equals 6, okay? And this will always be true. So the easiest way to solve a proportion like this one, I have 63 is to x as 7 is to 5, is I just cross multiply. So that tells me 63 times 5 is equal to 7 times x. And then I want to know just what x is. So what do I have to do? I have to divide by 7. Since I'm multiplying x by 7, to write an equivalent equation, I'm going to divide by 7. So I have to divide both sides by 7. So on the right side now I have x. And on the left side, I can divide out. 7 goes into 7 once and into 63 9 times. So I have 9 times 5. X is equal to 45. I can do a similar thing here. This is going to give me a little more complex, but here I can do 20 times x, so 20x. And that's going to be equal to 30 times 10 minus x. Whoops, why did I do 10 minus x? That should be x minus 10. Let's do that right. Okay. And now this left side is simplified. So to solve it, I'm going to simplify the right side by distributing 30x minus 300. And I want to make sure that I only have x's on one side. And since I have numbers over on the right side, let's get rid of the x's on this side and move them over to here. And the way we do that is we say, what's the opposite of 30x? Negative 30x. So I'm going to subtract 30x from both sides. On this side, I have 20x minus 30x. That's the same as 20 plus negative 30, which is negative 10x. Over here on the right side, the 30s cancel, positive 30, negative 30, and I'm left with negative 300. And then for that last step, here I have negative 10 times x. So to undo the negative 10 times, I'm going to do divide by negative 10. The negative 10s cancel on the left, giving me x. And then on the right, I have negative 30 divided by negative 10. Or sorry, negative 300 divided by negative 10, which is going to give me 30. So a value of 30. Let's check that out. If that's correct, that means I should be able to put 30 here. So 20 over 30 minus 10. And 30 where the x is over here. And sure enough, this is 20 over 20. That's 1. 30 over 30 is also 1. So it checks out. And we have just enough time for a couple of problems from last semester. Let's see. Whoops. Here we go. All right. So this was one that stumped some people. Bring this up. Which equations have solution set 2? So remember, for an equation to have a solution set of 2, that means if I replace x with 2, I should get a true statement. So in this one, you can see if I replace x with 2, I have 2 equals 2. That's true. So this equation has solution set 2. Let's look at the next one. Now if I replace x with 2, I have 3 times 2 equals 2. Nope, 6 is not equal to 2, so that one doesn't have solution set 2. So don't be confused just because there's a 2 on one side. That has nothing to do with the solution set, unless you have a simple equation like this one. For the last one, again, I'm going to replace x with 2. So I have 2 plus 1 equals 3, and that checks out. So this equation also has solution set 2. The other problem that stumped some people was this one, where we have to write an equation based on this information that we're given. And so we're told that Anne has X clients, Tim has twice as many as Anne, and Mara has 2 more than Anne. And in all, they have 22 clients. So I like to kind of read it again. And as I read it again, I'm going to start writing what I know. So Anne has X clients, so I'm just going to put an X there. Tim has twice as many. So you might automatically say, oh, I know what that means. But if you didn't know, then think about what if Anne had 3? How many would Tim have? Well, twice as many would be 6. And if Anne had 4, Tim would have twice as many, 8. And what are we doing to get from here to here? We're multiplying by 2. So twice as many just means 2x. Oops. And then we have Mara, and Mara has 2 more than Anne. So if Anne has 2, Mara would have 2. And for Mara's clients, we have x plus 2. The next thing that we want to do is see what other information we have that can help us solve this. We know that in all, they have 22 clients. In all means if I add up all their clients, I should get 22. So that means I can add Ann's clients, X, Tim's clients, 2X, and Mara's clients, X plus 2, and that should give me 22. Now I have a linear equation with one variable. I've got the variable X. And I can solve this by simplifying this left side by combining like terms. So I've got X, 2X, and X. So X, 2, this plus X. So 4X plus 2 is 22. And now I have X's over here, but I also have numbers over here. And I want to have all the X's on one side and the numbers on the other side. So I'm going to focus on that 2, and let's get rid of it. And we do that just by subtracting. What's the opposite of add 2? Subtract 2. So now over here, the plus 2 minus 2 cancel. I have 4X. On the right side, I have 22 minus 2, which is 20. And now we can do that last step. We have 4 times X, so we're going to do divide by 4. And then the 4 in the numerator cancels with the 4 in the denominator, and I have X on the left side. 20 divided by 4 is 5 on the right side. Now, am I done? Well, it didn't say what's X. It said, how many clients does Tim have? So first I'm going to go back here and figure out how many each of them has. So if X is 5, that means Ann has 5 clients. And Tim has 2 times 5, which is 10. And then Mara has 2 plus 2, which is 4. Let's see if that, oops, not 2 plus 2. X is 5. Better get that right. That should be 5. Okay. So Mara has 5 plus 2, which is 7. Okay, let's make sure that adds up to 22. So 5 plus 10 is 15, plus 7 is 22. Okay, that checks out. And the question was, how many does Tim have? And the answer is 10 clients. And that's all we have for today, but please, if you have questions, please reach out to either me or to your professor. You can find me at jane.keller@joyce.edu. Thanks for watching. Have a great day.